Okay, so what are we playing with today?
Analog digital conversion.
Analog to digital conversion. Okay. Well, I can give you a little rundown on A to D converters. They're fairly straightforward. They're actually really quite important. Okay, so a lot of what you're doing in this microprocessor stuff is dealing with transducers, and so you're trying to make some sort of measurement. You're measuring temperature or light intensity or all kinds of stuff like that. And you're trying to take this information from the real world and turn it into an electrical signal of some sort, and then you're trying to take that electrical signal and turn it into a digital number. That's the game here. So you have all these different types of sensors, and they all have their different properties. They all work differently, and you could do a whole course on, any three of them. But there they are. So
and that's done automatically.
This is the sensor itself, right? So
Yeah,
you want to measure. You want to measure temperature, right? So you can use a temperature-dependent resistor, or you could use a diode junction that changes characteristics over temperature and run current through it and measure the current. And you electrical guys, you should be seeing this stuff, right?
Yeah. Okay. Yeah, those are just our sensors, Nick, like the temperature sensor, the accelerometer.
Whatever you're measuring.
They automatically convert it into electrical signals for us?
It's a magical machine that does whatever it has to do through whatever magical properties to give us the measurement that we're looking for, and it usually puts it in some sort of electrical. It'll be a voltage or a current. Okay, so it's like a temperature. It'll be like 0 volts at 0 degrees Celsius and 0.5 volts at 50 degrees Celsius or something like that, and everything in between. Now I can hit space. Okay, so we're going to get from our transducer. We're going to be getting an analog signal. Can you guys actually see my mouse? Or
yeah, we can.
Yep.
Oh, okay, good. So from the transistor, you're going to get a continuous analog signal. It's an actual, genuine analog signal with an infinite number of. It's calculus. The calculus, right? It's calculus. It's infinite, continuous, has all the points. And we want to turn it into a digital signal. It's discrete and quantized. And you guys are going to do courses on how to do all this stuff later on, and the math behind all this stuff. It's going to be fun. But you can see how I'm taking that smooth sine wave and I'm turning it into this little stepped business here. Okay, so now there can only be so many levels, and there can only be so many, and it can only change. It can only make a measurement so quickly, right?
Based on your resolution.
Based on your sampling rate and your resolution. So the higher bit, like a 4-bit converter can do 16 steps, and a 16-bit converter can do 65,000 steps, and everything in between. If you want 10 bits or whatever, right? Mm-hmm. I think we're using a 12-bit converter, so it's goes for
14.
Yeah, a 14-bit converter. Okay, and so how many steps is that going to give us?
It's 16,384.
That's about right. So we got 16,000 steps up and down, and then we can run that thing like at about 100 kilohertz or something if you really let it rip. And that'll tell you how fast of a sine wave you can measure and all that type of thing. But at the end of the day, we're going to get a varying voltage going in, and it's going to be turned into a stream of numbers coming out. So each of these steps is going to have a number. So this lowest step is 0, and this highest step would be 16,000. It's just, here's a bunch of numbers. Mm-hmm. So here's a 4-bit conversion. And so we've got temperatures from 5 to 22 degrees Celsius, and all it's going to do is it's going to take a sample every day and decide what the maximum daily temperature was. And we want to sample that. And so, it's been a while since I've seen this slide deck. So say the temperature, I copied these from Robert Trost, who's the guy who normally teaches this course. And I redid the graphics and put it into PowerPoint. His was just a PDF. So it's his story. So this is calculating, so say the temperature was 9.5 degrees C on the 6th of February. So we look for the 6th of February. And we look at the point there, and we see that, it was around 10 degrees. And that even though the actual temperature was a little lower, it rounded it up because it was just above the threshold. So ideally, you're going to get this transfer function where it's exactly linear. There's a whole bunch of different types of errors that you can get from A to D conversions, depending on the slopes of the line and all that sort of thing. So at the end of the day, we got some math to do. We got our resolution. We talked a little bit about that, and it's basically the smallest detectable change in input. And so if you've got a to D converter that can go from 0 volts to 3.3 volts, which is what we got going on, so we're going to take 3.3 volts and subtract 0, so we're still 3.3, and we're going to divide that over 2 to the number of bits that we can convert. So we got 12 bits, so we got 2 to the 14, and so 3.3 over 2 to the 14. That will be the lowest voltage that you can detect a change. So if you put a voltage in and you increment it by that little bit, you should get one higher number.
That's your step voltage, right?
Your step voltage. That's the voltage. Yeah, size of the step. That's the resolution.
Okay, so the range min, the book says you can change the range min. That actually can be assigned. It's automatically 0, but you can change it to something else.
Oh, you can also feed in external voltage references and all kinds of other stuff. It slices, it dices.
Okay, and the reason for that would be what?
To closer, you've got a temperature sensor that goes from 2 volts to 2.5 volts, and you want to really.
Oh, okay. So you never actually go below 2 volts. So in that instance, you would just make your range min. So it's like,
yeah, that type of thing.
Okay.
And then doing that increases your resolution, right? Because then
you're zooming
smaller
in
voltage. Zooming in.
Yeah, you're zooming in, but you're increasing noise, and there's all kinds of other trade-offs, but we won't go there because that's a whole other course. Anyway, resolution, and then you got your quantized value. So the numeric output is your number of bits times whatever input you're given minus the minimum divided by your range. Okay, and that'll give you, basically the value you're going to get. So if your converter is running from 0 to 2 volt, or from 0 to 2 volts, and you put 1 volt in, then it's going to be basically 8,000 or whatever, half of our bit resolution. Okay, these are a bunch of different types of errors you can get. Quantization errors, like the offset error, where your reference is out a little bit, and so everything's all just shifted. You can get some gain error where it's starts to diverge, and you can get various other nonlinearities and things like that. Most A to D converters that you're going to play with, you lucky people, have most of that stuff down to almost nothing. But if you are doing something particularly, where you really are trying to do a very tiny signal and it's got to be super ultra precise and all that stuff, then you may have to take some of this stuff into account. A lot of the time you can ignore this. It depends on the nature of your application. Okay, here's a simple summing circuit. So all we're going to do is take four different signals, and we're going to take their voltages and sum them together, amplify it a bit, and then stabilize it. So this is just a buffer, basically. This is a simple digital analog converter. Okay, and a digital analog converter is the opposite of an analog to digital converter. So in an analog to digital converter, we want to take a voltage coming in, and we want to turn it into a number. Well, here we want to take a number and turn it into a voltage. Mm-hmm. Okay, so we're going to write this number on B0, B1, B2, B3. Okay, so if we write like a 16-bit number here, it's going to sum these voltages, right? So this one is going to give us the lowest bit, so 16 times R. Is this working? Hello?
Yeah.
Yeah.
Yeah. Okay. So if we put a 0001. Okay. Well, if we put 0000 on there, this would be 0 volts, and that would all amplify out. We get a 0 volts out of here. If we put like a 1 at a 000, then that would give us a tiny little voltage, right? Because the 16R and then all that stuff. If you actually figure this as 5 volts and 5 volts and 0 volts. So I either put 5 volts or 0 volts. So I put 5 volts here, 0 volts here, 0 volts here, and 0 volts here. And if you did the math, you'd end up with a certain tiny voltage. This math right here. And that would be our 1 bit. And then this would be the 2. So if we want to go to 2, we turn that to be a 0, that to be a 1, and all the others to be a 0, and all the other combinations for binary. You must know how to count by binary now. And effectively, this is going to, depending on what combinations of zeros and ones here, is going to give us a voltage out of here that's going to be basically a D to A conversion. It's going to take this digital number here and convert it into a voltage there, right?
Mm-hmm.
Did we lose you?
No, I think we've done circuits like that just in our labs for other classes.
Okay, well you can say go quicker or go slower if you'd like, because I I don't know where we're at here. Okay, so this block right here, this digital analog converter, is that other block, right? Mm-hmm. And we have like a Digi2 up counter going on here, a ripple counter thing, and it's got an enable, a clock, and a clear. Okay, so when we want to start conversion, we can just clear this counter and it'll all go to zeros, which will put a 0 on our D to A, which will give us a 0 for the comparator reference. Okay, we're going to compare our analog input against that reference. And if it's higher, then we're gonna enable the up counter, and the clock is going to clock it one more clock, and now it's going to have a slightly higher conversion, or slightly higher reference, still be enabled, and eventually this will count up to a certain point at which this comparator says, no, it's definitely, we've hit it. See, we've counted up, we've stepped up, and we finally hit the voltage that we put in. And so now we're going to stop counting. So we disable the counter, so it stops counting. And that becomes our signal that the conversion is complete. And if we want to read the results, we just read the number off of the output of the up counter, and that's our conversion.
Mm-hmm. Okay. Now, this isn't like the one that we have in our chip, right? This is just a simple version? This is
as simple as you can get. And it's very slow because they have to go one step per. It's a different conversion time.
And it also seems it's counting from the lowest value up, right? Or from the least significant bit?
Yep, and it's doing it naively. So if you had like a big 65,000 step counter, you'd have to do 65,000 clocks in order to get all the way to the top, and it would take a different amount of time depending on the voltage.
Yeah. Okay.
And so, but it's there. It's simple. It's easy to understand. Makes sense, right? This is another kind of fancier one. This is kind of how CD-ROMs or like CD-ROMs, CD players work. You know, normal those old things from hundreds of years ago, the little shiny discs.
Yeah.
You must remember that. You guys are probably old enough to remember those.
I think us two are old enough.
Anyway, they use what's called a sigma delta converter, or delta sigma, and it's really only got a 1-bit conversion, but it's kind of a funny thing, right? So now instead of just an up counter, we've got an up and down counter. And it's going to start at some value, wherever it is. And it's going to say, well, is the thing we're trying to measure higher or lower? That's lower, well, I better count down. Is it still lower? I'm going to count down some more. Oh, okay, now it's higher, now it's lower, now it's higher, now it's lower. Oh, lower, higher, lower, higher. And what you end up with is a stream of bits coming out of here. And you can basically read them, and you can use that to encode your wave.
Mm-hmm.
It's an interesting, clever way to make high bit count converters, because you're the way you get a higher quality converter is by using a lower noise system. So if you can make the, if your comparator is 0.00000% and your signal paths and stuff are all set up so that they're ultra low noise and you've taken into account all the little capacitances and inductances and all that stuff, and you got it to the point where you can get 16 bits of conversion, then, well, there you go. You got 16 bits of conversion now. If you can make it a little better, you can get 20 bits or 24 bits or whatever. And so it's limited more by the quality of the signal paths and chains and the quality of electronics. But again, that's not the kind we have. Now there's another kind which is called a flash converter. And this is where is basically you have
that would be like parallel in, serial out, right?
Yeah, that's the parallel in, serial out. You basically get it in one clock site. Here's your strobe, and you say, okay, everybody, you compare. Here's a little R network, and basically you get an instant answer. Basically using this, there's some magic gates in here to decode these outputs and decide which one of them won, and that gives you your 2-bit output.
Now with this one though, like it can read the whole voltage input in one clock cycle, but it can't output it all in one clock cycle, right?
It's not outputting. It's outputting a binary number, which
right.
That just happens. And
right.
You guys still see my camera?
Yeah. Yeah.
Okay.
Right. Yeah. Okay, that makes sense.
Yeah. Okay. So this is closer to what we have.
Yeah.
This is successive approximation, and it uses some instead of a counter, it actually uses some fairly fancy sequential digital logic, which we won't go into. But you could think of it as still performing the same function as the counter, because all the rest of it is pretty much the same. And it's going to test each bit individually. So, and you get the same conversion time because it's basically your clock cycle. It's got to convert like one clock cycle per bit, at plus maybe some. And it's simple, compact. Conversions are quick. They always take the same time. It's by far the most common type, and it is the one that's being used on our device. And it looks a little like this. So you're going to set the most significant bit. You're going to say, let's make the highest. We're going to test to see whether it's a halfway point. It's the most significant bit. It's going to be 50%. And if it's greater, well, then we're going to leave that bit set. And if it's lesser, we'll clear it.
Other way around, I think you mean, right? If it's less than, then it's going to keep it set and then increase the next one.
Nope. If you're measuring.
You're talking if the VN is greater. Sorry.
Yes. Sorry.
Okay.
Yeah.
I was thinking the other way around. Yeah.
Okay. No, that's fair enough. Yeah. Yeah. Exactly. Thank you for clarifying that, because I don't always see stuff like that. I'm left-handed and a little dyslexic and who knows what. So sometimes that stuff just sends me going around in circles. So if there's ever one of those going on, feel free to let me know. So yeah, so basically it's just using a comparator, and you're just saying, okay, well, the VN is higher than what my reference, and so I'm going to leave this bit set, and I'm going to set the next bit, which is going to now set the reference to be there. And then I'm going to do the compare again. I say, oh, no, it's lower now, so I'm going to clear that bit. Puts us back down to here, and then I'm going to set the next bit, which puts me to here. And so on, until eventually it converges. And we do that for all the bits until all the bits have been tested, and then whichever way they got left, that's their answer. So most of the ADCs are, from the point of view of the processor, very, identical. You got start a conversion bit, you got an end a conversion bit, you got your actual digital output, you got your voltage in, and you got a clock. So they'll all have the following: voltage input, upper voltage reference, lower voltage reference, clock, start a conversion trigger, end a conversion flag, and some output. Okay, doesn't matter which flavor of ADC you can basically abstract it away, other than its specific properties as a number of bits and how fast it can be and all that stuff. But you can abstract it away to basically this set of stuff. Okay. So we have an 8-bit ADD converter with 10 volts reference high and a -5 volt reference low, and it's giving us a digital output of 42. So now this would be like a question on the exam. This is actually a question I put on my exam. So we got to figure out what voltage was applied. And so we're going to take our 42 volts in and get our, we don't know what the VN is, but we're going to put all of our references in, and we got our bits, rearrange it, do all the mathy stuff that you guys do probably in your sleep by now, and you end up with that as a voltage input.
Okay.
Okay. It's pretty straightforward. It makes sense. There's not really anything, magical to it. And compared to all your Laplace and all that other crap that you guys are doing, this is nothing. There could be an error of plus or minus half a bit, depending on where that last compare ended up. Okay, so you got a certain voltage in, and you can really only your digital output can say it's either there or it's there. Like your digital output says here, so we got our 42. There it is. Well, potentially there's an error.
Yeah.
Okay. Now that might not sit in the middle like that. It actually might sit up here, because of the way the converter works, or the comparator works, is only comparing whether it's above, so it might shift it a bit. But essentially, you can think of there being an error there that's a potential error. So again, depending on how much you care about that, like it depends on the nature of your application. So we want to be able to calculate our resolution and our quantization error. Typically, we'll call it a half of a bit and just call it done. Okay. So you should be able to, given a certain VREF high and low and a certain number of bits, you should be able to easily calculate out the resolution. And from that, you can calculate the quantization error.
Would you need the error worked into your final answer on that too? Like it would have to be negative 2.5391 volts plus or minus 29.3 millivolts, or?
Well, it depends on how much you want to sound like an engineer. You want to sound like it depends. Again, Okay, the good standard answer to all this stuff is it depends. Again, it all depends on the nature of your application. But
boom, there it is.
Okay. So now we got a different type of problem. We got an 8-bit ADD converter with the same reference. And, well, what if we put 3.1 volts into it? What will we get? Well, there's our formula. You start plugging stuff in. So it would give us a decimal number of 138. Okay, so you should be able to do that calculation in your sleep too. Okay, so sampling. So say your voltage is changing. So all you can say is while the ADD conversion is going, like you're really trying to only look at that one step. If the voltage is actually changing during that step, then you don't know what's going on. So they do a circuit in front of it that does what's called a sample and hold. And what it is a little capacitor and a little FET that you turn the FET on and the signal goes in and charges the capacitor up, and then you turn the FET off, and then the capacitor just holds that voltage for a while, and then that's the voltage that the A to D converter works on, so that the actual signal isn't changing while you're doing the conversion.
And you say that's just using like an RC where the capacitor kind of holds the charge and it doesn't lose the voltage right away?
Yeah. Yeah, it holds it long enough. It doesn't change enough. It doesn't change enough to matter, and holds it long enough to for one conversion time, so that it's the input voltage is stable. So that's called a sample and hold. Okay, and the sampling thing is saying, okay, we're at the beginning of the step. We want to make a conversion, so let's freeze the voltage, figure out what that voltage is, and that'll be our number for this step. Okay, that's sampling. And then you got sample and hold. And then you got the sampling rate. Okay, so if you got and you're going to do courses, much more stuff on this whole signals and systems and all that stuff. You'll cover this stuff 4 or 5 more times as Nyquist. I don't know why he really covers it in this course as much as he does, but we'll talk a little bit about Nyquist, which is the fact that if you had a sine wave going in and you were trying to sample it, there's a minimum sampling speed in order to be able to recreate the signal. Okay, and it's called the Nyquist-Shannon sampling theorem. You can look it up. There's a whole other bunch of stuff. But the gist of it is if your sampling rate is 100 kilohertz, then the fastest sine wave you could sample is 50 kilohertz, because that would hopefully get you one at the top and one at the bottom, but it would really only end up looking like a triangle and kind of sucks. You'd actually want a little bit more than that. And it's a whole other topic. Okay. Anyway, that's the talk about A to D converters themselves.
Mm-hmm.
Any idea what we're looking at?
Record.
Yeah. Yeah, vinyl.
Yeah, tiny little bumps.
And those little bumps are what you're trying to measure.
Yeah.
Okay, so that's A to D converters in general. Any questions about that?
No, I understand them. Okay, it's more just setting of the registers now.
Okay, well that's this one. There we go. Oh boy, the MSP 432, which I really do like, ADC 14 and everything. Precision ADC 14. 14-bit SAR. You can get up to a mega sample.
How does that time work again? So 1 million samples in a second?
You betcha.
Okay,
1 million samples.
So if we have like 9 clock cycles, then it's going to be divided by, or times 9 or whatever.
Well, you got more than 14, because it's at least one per bit.
Yeah. Okay. Sorry, I was thinking of the 8-bit because it asked us in the pre-lab for an 8-bit.
Yeah.
But for 14, we have 16 cycles.
Yep. Yeah, I think there's an extra couple.
Okay.
Conversions can be initiated by software, so you can have a thing where you set a bit and say, okay, start conversion. Or you can actually set up a timer to actually start the conversion, if you want to do it regularly. And that's how you would do it if you were trying to sample audio or something like that, is you'd set up a timer so that you always get a perfectly timed sample start. Because if that's all jittery, then when you go to play it back, it's all going to be a little jittery and it'll not be good. Built-in software selectable reference voltages, so you can actually set different reference voltages, and for our purposes, we probably use 2.5 for a lot of it. And it's got a sample and hold with programmable periods, so you can set it to sample and hold for a long time or a short time. It's got 32 inputs, so you can actually have 32 different voltages. You can only ever sample one at a time, but you can have all 32 of them all there and say, okay, get that one, get that one, get that one, get that one, get that one. You can use single-ended or differential inputs, so either a ground reference signal that just changes, or you can have a plus and a minus like on the input of an op-amp. It's got a temperature sensor built on chip and a way to measure VCC, so you can actually measure the power. It's got a window comparator, so it'll actually, you can actually set it up in hardware to watch a voltage, and if that voltage ever goes outside of a certain window, it'll generate an interrupt. It's got 32 storage registers and a whole bunch of different conversion modes where it'll do stuff automatically for you. So you can either do a single channel conversion, and they say, okay, start conversion. Okay, you're done. Okay, give me your number. Yeah, that's good. Okay, well, start conversion. Where's your number? Okay, thank you. And it's like a very mechanical thing. Or you can do repeat single channel, where you say, okay, start conversion, and it'll sample that one channel, say, okay, here's a number for you, and then automatically start again. There's another number for you, automatically start again. So you just keep doing the same channel. And it'll also do that with more than one channel. So you can do a sequence. So you can say, okay, get a sample there, sample there, sample there, sample there, sample there. Now let me know when you're done. I'll take those 5 numbers away, and then we can do it again. And it's essentially a manual or auto version of that. It can generate 38 different types of interrupts. So there's ways to hook on and get interrupts from 38 different types of events. It's quite a complicated little beast. It's a wonderful machine, and it's fun once you start getting it figured out. But for someone who's never had to deal with this type of stuff before, it's a beast. So you start with some reference voltages. So that's all this whole section up here. It gives you your 1.2 volts and all that. And this is the bits in the register that are setting what that reference is. So, or you can have I think there's an external. I think that's these pins here can be actually. Oh no, here it is. Oh no, it's in here. These ones would be where you could apply an external voltage reference. Or you can set various combinations of things to be able to get references out and all that stuff, blah, blah, blah. Then you got the clock. Well, we got this clock in order to clock the bits. Well, this clock system is very similar to what you had with the timer and the PWM, where you get to set whether you're using the system clock or M clock or the A clock. As an input, and then it's got a couple of levels of divider in front of it, so you don't have to be, so you can chunk it down, and then that actually drives this 14-bit core. So this is yeah.
So the 1 megasample per second, is that like its maximum speed then? Does it?
Yeah.
It depends on the clock though, like which one you put in, that what it'll do.
You'd set that clock and then divide it down in such a way that this ended up being a megahertz right here, right? Okay, and you can see that that's driving the ADC core. It's also the sample timer, which does the sample hold.
What happens if you like run in the MS clock or SM clock at like no divider then? Because that's 3 megahertz, right?
Well, it probably wouldn't work very well.
Yeah, just get errors on the conversion and stuff, or.
All bets are off. You probably, you wouldn't have heard anything. It just probably wouldn't work, or it would work very funny, or I'm not really sure.
Yeah.
So how do we determine which sampling rate to use then?
Well, okay, your labs are going to be looking at pots, right? Joystick or whatever.
Joystick.
Which is like very, 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 very slow.
Yeah. Because it's like as fast as you can move the joystick, right? So
it's insanely slow. So it almost doesn't matter what your sample rate is for this application. Where the sample rate starts to matter is if, say, you were trying to record audio or video or something like that. Well, audio specifically. Your sampling rate would determine the highest frequency that you could record.
And so sample is the time it takes to convert, or is it's the time it takes to send one bit?
That's how wide one of the steps is.
Okay.
Yeah.
Right? It's not how tall it is, it's how wide it is. So
yeah.
Only so many of them steps per second. Each one is a sample and you get to be here, 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 but it's like you're slicing it up. So this 14-bit ADC core is basically what we just talked about in the last slide deck. It was all basically in there. And so you can see we're giving it a clock and we have our reference voltages. Well, there's also the sample and hold. And it's taking a signal from this multiplexer. These triangle things are multiplexers, right? And so what this multiplexer is taking all of our inputs from all of our pins, as well as some like onboard temperature sensors and ways to calculate the battery voltage and all that sort of junk. So that's what all this other stuff is down here. And this whole machine sits there anxiously waiting for a signal from over here, which is our start conversion. And that's a bit in a register. Okay. But you see, it's also hooked up to a multiplexer, so there's actually a bunch of different ways of starting conversion, and these other trigger sources are timers and things like that, where you can have a timer do the start conversion, or this bit.
And that's basically just the enable bit for the whole thing, right?
Well, that's just like the knocking over the first domino.
Yeah.
Say, okay, start conversion. It's like, oh, there's your answer, right? But
it remains off without that one activated.
Yeah, it just sits there going, okay, I'm all ready. All we got to do is say go. The mouse trap is all set. If you ever play mouse trap,
yeah.
Mouse trap's all set up and ready to go. All we got to do is turn a little crank thing until it. Okay. Anyway, that's the trigger, the first domino, and of course it can come from more than one source. And then at the end of it, after like it churns and chugs and does whatever it's going to do with whatever inputs and whatever references and whatever clocks and whatever sample timers and all that stuff, eventually it's going to give us this bit here that says, she's done.
Mm-hmm.
The number's ready for you. Now what happens is when the conversion is done, it gets written into this memory bank. There's 32 channels, and each one is a 16-bit register.
Oh.
Okay, so you get mem0 to mem31, and that's where the converted number ends up. Okay, now each one of those memory channels actually has a control channel with it too. And then, okay. That's a quick little tour through that. This diagram is available in the Family Reference Guide. I would also recommend you take a look at the chapter on ADD converter and actually read the first couple pages just to, even if a lot of it goes flying over your head, you're still going to pick up stuff.
Yeah, I read through that section already too, and it's just like the control, there's so much to the control register alone that's like trying to figure it out is.
Well, once you see this diagram, you should probably, the control register already start making a bunch more sense.
Yeah, that's true. Yeah.
Right? And you start looking at it from that point of view and you say, okay, well, here we're just checking the clock, and here we're just setting up this, and here we're just setting up that. Mm-hmm. Okay, sample and hold. So it makes it steady. So, okay, we didn't talk about sample and holds. Okay, so there's your capacitor we were talking about with the FET. And so when the switch is closed, this capacitor is just going to follow the voltage of whatever the voltage is, and when that switch gets open, then there's nothing to drain the cap, so it'll stay just at the same voltage presumably for a while, a little bit of leakage or whatever, but okay, so we got this continuously analog signal, but we want to hold the voltage and look at these samples, right? See what's going on there? Yeah, here's all of our registers. Again, another chart that once you actually start getting in tune with how this stuff works and you start getting used to it, ultimately you end up just looking at charts like this because it just tells you the whole thing in one shot. So you can see we got a couple control registers, a bunch of comparator registers, which we're not going to use that feature. We got memory control 0 to memory control 31. So there's these 32 registers here. Memory 0 to memory 31. There's these 32 registers. And then some interrupt register enable some things.
Sorry, Stephen. So each one of these registers is just 16 bits, right?
That's correct.
Okay, so the control 0 and 1 are tandem, like you have to program them together.
Well, they're two different registers. You see the offset here. So offset 0, this is like 4 bytes away from it.
Oh,
so
okay.
this is actually a 32-bit register.
Oh, okay.
They're actually,
Okay,
yeah.
gotcha. So they're 32s.
I guess so, yeah. Okay, control 0. And then a little mnemonic here. Look at that. See, it's 32 bits.
Wow.
Just to make it extra hard. This is a 32-bit processor, so nominally its favorite way of addressing memory and stuff is 32 bits at a time.
Mm-hmm.
Well, okay, this first bit here is very important. This is the enable conversion bit. Okay, it's different than the start conversion. This is basically the enable.
Oh.
And the way I like to think of this one is it's the clutch.
Yeah. So if you changes, you gotta
put the clutch in and just shut everything down, make whatever changes you want, and let go of the clutch, and then it'll all start up again, right? Okay.
Yeah.
So that's what's going on there. That's the enable bit, enable conversion bit. And you're not allowed to, if you disable it, you got to disable it for at least 3 cycles. I guess you're not going to run into too much trouble with that. Power on can only be changed.
So you have to have power on and enable and start conversion.
Yeah, you got to disable. You got to disable you got to put the clutch in. Then you can turn the power on. Then you can let the clutch out, and the power will actually go on.
Is it actually critical, like the order that you write these in on the register, or no? Because it's all at once.
Well, typically with the exception of the clutch, it'd be all at once. So usually I put the clutch in as a separate instruction.
Oh, okay.
And I give it that extra little, the one cycle, a little extra few clock cycles to actually be,
okay,
to kick in. And then you can basically load the registers any way you want, as fast as you want, whatever, all at once, whatever.
Mm-hmm.
So those are the important ones out of that whole register, right? After looking at all that, so the rest of this stuff is setting the sample and hold times and setting the clock dividers and the clock sources. I guess there's a busy flag in here we might care about a little later. Okay, but if you actually look at what the rest of this register is doing, it's mostly just setting up the clock and all that stuff.
Does it picks a clock just to start with too if we don't set one, right? It's got like a preset.
Okay, well, if you look at these yellow bands, that's your bit number, right? So this is the lowest bit, this is the highest bit, and then these gray bars are the function. And then you see under here it says RW-0, RW-0.
Yeah, read write or set
well,
to 0.
read write says, well, you can read it and write it, whereas like if you look at this busy flag, it's just got an R.
Okay.
So you can't write. Doesn't matter what you write there. It doesn't matter, right? It doesn't care, right? But when you read it, you're going to read it. Okay. Same with a couple down here. Like you can write anything you want here, but every time you read it, it's going to read a 0. That's all you get. Okay. So that's going to tell you what the register will be set to when it is powered up.
Okay.
The -0 bit. Sorry, we did the read write, and the -0 bit says what it's going to be when it's powered up.
Oh. That part I didn't know.
Yeah, so in this case, in fact, I think this number here also says it. The 0H is what it is when it's powered up.
It's like preset value. Okay.
Yeah, it's preset. Okay, and these gray ones are bits that can only be modified when this is set to 0.
Oh.
So all of them.
Yeah, basically all of them except for the start conversion and get busy. Because
you can't even write those. Yeah.
Well, you can write start conversion right in code, but that's it.
And you probably don't recommend, like you said, always do that control or enable.
Yeah, you can pop the clutch with your last write if that is truly your last write. But typically, I wouldn't re-enable it until I've done all the setup for the whatever I was going to do.
Mm-hmm.
So you don't need to have the clutch in order for this thing to go, though.
Well, you got to have the clutch out for it to go, or it'll you'll be revving your engine doing nothing.
Okay, so when you start the setup for this, you have to enable it and then change the bits and then disable it.
Other way around. You set the ENC bit to 0.
Oh, that's enabling it. Sorry.
There you go.
You disable it.
You disable it. So you set it to 0, and then that's a separate instruction. Then you do whatever setup you're going to do for the whole thing, and then you can set it the other way around. So you set it to enabled, and then after that you can start doing start conversion. So you got to do power on. And okay, so this is the other register, which I don't think has much. You can set the resolution. You can actually get away with shorter clock cycle conversions. Like your application might only need 8 bits, or the less bits, obviously, you can do a faster conversion. That type of thing. So there's reasons that you could change this from a 14-bit to an 8-bit, or to a 12 or 10. And
yeah, like I guess more likely for like temperature sensors, you're going to want like less bits, right? Because it doesn't matter as much. It doesn't fluctuate.
Depends. Well, the fluctuate part's fine. It's just how precise do you have to measure the temperature?
Yeah.
Okay. All right. If it's a living room thermostat for a furnace, then maybe 1 degree is fine. If it's some chemical process in a factory, then maybe you need 1/100th of a degree or some silly thing. Don't know. Now, every one of those, there's 32 registers that the answers can be put into, okay? And they're like a little memory bank of places for the ADD conversions to go. Each one of them has its own control register. So there's it's actually pairs.
So this is just like a way worse timer.
yeah, it's kind of like the timer thing.
Yeah.
Where it's got its own individual. It's kind of the same deal. Only you got 32 of them. They're identical though, so it's not that bad.
It's not like the 0 is different than the other ones.
Yeah, and there's none of that stuff. I don't think. Mostly, what this is going to set, as you can see, most of the registers are empty up here, and a lot of this stuff you're never going to touch. Mostly, the only one you're going to touch is this bottom set, and potentially this bit here. Essentially, you could look at each one of these registers as being one conversion. Okay, and so you're going to set like what channel you're going to convert, and you can also set what reference you can use to convert that channel, and it can use a different reference. Like so this channel uses this reference, but we could make a different reference for this channel because this channel is different than that channel for some reason, right? So this is what this is doing. Is it sets with the voltage reference. Most of the time, you're just going to leave that. And then what these bits set is which channel it's going to use. So basically what pin on the processor. So this A1 to A9. oh yeah, this is whether it's diff or not. Yeah, this just sets the channels A1 to what's going on here? Oh, here it is, A1 to A0 to A9. Yeah, and this diff bit decides whether it's a differential or a single-ended. So if it's single-ended, you have a ground reference, and then the signal just is reference to ground. And if it's differential, you basically are measuring the difference between the two voltages, and they're two pins per one. So that's why it makes this pattern here.
You're losing me here, man. So
so the inputs to the converter, yeah. Sorry, I know I'm babbling here, going around in circles. I don't have a good picture for it. The input to the converter, the voltage that you're actually going to convert, can either be single-ended or differential. If it's single-ended, it's basically essentially with reference to ground or with reference to the negative reference in this case, but with reference to ground and just a single voltage and a single pin. So everybody has the same ground and your voltage is reference to ground, period. Okay, so you got one signal, one wire. In a differential, you actually have a plus and a minus, and it's like the input of an op-amp. And the output of that is what you're converting. But you actually have two pins. And
so it's comparing the difference between the two of them.
Yeah, it's a differential signal. It's not reference to ground per se anymore. It's more the difference between them.
I wonder,
using that as a conversion, and so that's why you end up with half the channels. It's like you end up with just the odd ones. Okay.
Trying to think of a good example for that.
There are like for instance, if you're measuring something that's at the end of a long wire.
Yeah. So you want to measure the signal at the start and then what it is at the end or something.
You got a 50-foot wire, right? And if it was just ground with a signal wire, any radio noise that hit that wire would impose a voltage on it, and it would be all over the place. If you're using a differential, you end up with they cancel out. So the signal hits those both wires at the same time and causes the voltage to change on both wires at the same time, but the difference between them doesn't change. And thus you end up with a much cleaner signal. So that's why like microphones and stuff tend to be differential.
Okay.
They're in the end of a long 100-foot wire, right?
Yeah.
And even if you shield it, it's still going to be crappy. Oh yeah. Anyway, suffice to say, you can have single-ended or dual-ended. For your labs, forget about the differential. Who cares? It won't even be on a test.
Yeah.
But just if you happen to actually be really using one of these for something and you run into a situation where you need a differential input, hey, it's got it. It complicates the slide a little bit, but otherwise it's got it. At the end of the day, essentially, this set of bits down here sets the channel, and that's really all you got to care about. So you're setting, if you actually look at the pinout of the processor on the data sheet, you'll see actually it says A0, A1, A2, A3. Okay, and so that's essentially what's being mapped. Whatever. Sets the channels. And here's a hint for you. As I started, I actually got the first two labs marked. I'm partway through marking the third lab. Yay! You get no magic numbers, right? So do the define. So you define joystick X, joystick Y, whatever temperature, whatever, and set the channel number. And then when you go to write it, you can say ADC14 M control, which is this register, and then whichever one you want to change to be that channel. Okay, and you can only do it with the clutch in. You can only write to this register with the clutch in, right?
Okay.
All right.
This is gonna get confusing.
Well, just remember the clutch. You'll be halfway there. Okay, now this is interrupt flags register 0, and it's got 1 bit for each of 32 input registers. So like you got 32 slots that you can have answers go into, and depending on how you set the M control, that'll set which ones get used and which ones get hooked up to what channels and what references and all that stuff. And then this register will tell you, we'll put a 1 bit on when that memory register gets written with a number. Okay, we'll get there. Okay, this is just telling you which of the, like you got. It's a one of those mailbox things where you got the slots that you can stuff an envelope into. Okay, you got 32 of them. Okay, and you're going to say, well, you know what? We're not even using all of those. We're just going to use these 3, and this one is for me, and this one is for you, and this one is for the other guy. And envelope comes in, and it's for me. I put the envelope into my slot, and then the bit turns on in this register saying, hey, there's something there for you. And then I put something into your slot, and the second bit turns on and says, oh, there's something for you. And I put one in the third slot, and it says, oh, there's something for you. The conversion's done, right? And when I pull the envelope out of the slot and read the value, get the number out of the mem, then this flag will automatically be cleared. Okay, magic bit of code there. So we have a certain channel number 2 or whatever, and I want to wait for the sample to be done. I can say, well, and I'm going to read this register, this interrupt flag 0 register, and I'm going to AND it with a 1 shifted by 2. I'm going to have a 1 shifted by 2. I'll be on channel 2. And then, well, while that's 0, well, like a 0 is false. So while I do this ANDing and it ends up being a 0, that means that bit is still 0. So while that's true, just sit there and wait.
And that continue in the squiggly brackets is just
that's just
a wait, kind of.
Just a wait. That's continue. Continue is the opposite of break. You could put just a semicolon there, and that would be fine. Except for it's a common newbie mistake, so I would recommend the brackets. You could put just a pair of open closed brackets, and that's fine. But it's a little boring, so you could actually put an open bracket semicolon closed bracket, and that'd be kind of okay. But if you actually put the word continue in there, you're basically saying, I definitely mean for this to be a busy loop. No question about it. Okay, they're all the same. They all generate the same code. They're all basically a wait loop.
Okay.
How to set up for single conversion. Now we're getting to some meat here. Sorry for taking too much time here, but this is hopefully clearing some stuff up for you. You got to set the pin to be, you got to do the cell stuff. Remember SEL? How that worked? Okay. Because we're not using those pins as general purpose input outputs anymore. Now we want to have them hooked up to their internal function.
Yeah.
Okay, so we got to program those the right way. Then we got to set the control registers 0 and 1. And so we want to turn on the block and make sure the enable conversion bit is cleared, and set our clock sources and divider, set our conversion mode, whether we're doing the single conversion or the single conversion repeat or whatever, set the sample and hold time, set the conversion start control source, whether we're going to actually hit that flag or whether it's going to be converted automatically from a timer or something. We're not going to play with timer stuff, so you don't have to worry about that.
Yeah.
Set the resolution. I recommend just winding it out full blast because why not? Set the conversion start address. Well, the conversion start address is the address of the memory number that it wants to start converting at. So normally it would just start converting at 0, and if you did, yeah, you can set up a little chain reaction where it finishes conversion. If you set it in the auto mode or whatever, it'll start converting on the first register, and then fill that, and then go to the next one, and the next one, and the next one until it gets a stop bit. So you can set up these sort of little cascades if you want to do a bunch of channels at once. What the start address does is it just says whether it's starting at mem0 or starting at mem5 or starting at mem6 or something like that. Most of the time you just leave it on 0. Then you're going to set the reference voltages in the control register for the memory, and then you're going to set the channel number to sample for the mem control. So you see how these first bunch are in the control registers, but these ones are in the memory control registers. They're two different things, right?
Okay.
So there's like 32 of these ones. It's like, think of each one as being your channel for sampling. Right. Now you're going to use single channel sampling mostly, but if you want to do fancy, like for the joystick, you got 2 voltages, right? So why not get 2 voltages in one conversion? So it'll automatically do the 2, and then say, okay, I've got 2 new numbers for you. You ready? And otherwise, all that happens automatically. Anyway, so now we've set up the converter. So we've set all that. We can now start running the thing. So we're going to initiate the conversion, and going to make sure that the enable conversion bit is set, and then we set the start conversion bit, and we wait for the interrupt flag, wait for it to be finished, and then read our result. Do whatever we want to do with the result. So this would be a typical input signal. You got a pot. This is what our joystick looks like. It's got ground on one side. It's got 3.3 volts on the other. And then it's a pot, and it's just hooked up to a port pin. Sample code. Okay. So we got some certain channel we want to connect to, and we can say, look that up on the data sheet and figure out what pin it is. This is shutting the watchdog off. This is putting in the clutch. This is going to turn the power on, but it's going to make sure that ENC goes to 0 at the same time. So this is basically powering up and putting the clutch in. And then this is setting it up to be single channel conversion, and setting a 32 cycle sample time. And
sorry, do you mean the ADC14 control 0 equals ADC14 control 0 on?
Yeah.
Is that just because the enable is started as a 0? Like that's why it's kind of doing that?
Well, okay, this is doing a write of the whole register.
Yeah.
Okay. So, and this on bit is just one single bit. It's the power bit.
Yeah.
There's one bit, and all the other bits are 0.
Okay.
Including the ENC bit.
Yeah.
And it's writing them all at once. It's like, because it's equals here.
Yeah, and sorry, so the enable had to be set to 0 in order to write the other bits.
Yeah.
Okay. Okay.
Yeah.
Got it.
And this will do the power up too.
So you basically have to turn power on and then do the other stuff.
Yeah.
Okay.
And now we got power on, and now we're setting up where the clock is, and single channel mode, and the sample time. And we can set CTL1, we're going to set it to be a 10-bit conversion instead of 12 or 14, just because. And then here we're setting memory control 0. And really, we don't care. The references and all the other stuff in that register are fine to be 0 bits or whatever. So really, all we're doing here is we're setting it to be the channel number. So really, all you got to write to the mem control is the channel number if you're only doing a one single channel conversion, right?
Okay.
And then here we're actually letting the clutch out.
Yeah.
So this time we did an OR equals because we don't want to change the rest of the bits. We just want to just set that one bit on, right?
Oh, okay. I see the difference. Right. Okay.
Okay. We're just going to set that one bit on,
first
right?
we just said equals. Okay.
Yeah. Okay. And then here we're going to set our P51 to be used as an analog input. That's our channel number here. This is the cell stuff. You guys know how to do that stuff, right?
Yeah.
Okay. So now we're going to fall into the while loop. And we're going to another or equal here because we don't want to mess with the rest of the thing. We just want to set this one bit. Where's the start conversion bit? And then here we're going to wait for that conversion to be done. And then there's our result. We're going to read it out of the memory. So here we're setting M control 0, our sample number, M control 0, and here they were reading out of mem 0.
Mm-hmm.
The mem is the number that we've converted.
Okay.
Clear as mud?
Sorry?
Is it clear as mud?
Yeah, can you repeat just that last bit? So you're using the M control for channel 0, and that's why you're looking at the memory for 0, right?
Yeah, because they work as a team. Right?
Yeah, okay. Okay, got it.
Okay. Now when you're setting up the cascade, you would set up the mem channel. If I go back a bunch, here we go. If you set up the cascade and you set it into multi-channel mode or whatever it is, then it's that say starts at 0. Just will not change that. So it starts at 0, and so you'd set the channel for channel 0, and you set channel for channel 1 and channel 2, channel 3, or whatever. And so you're setting that for each of them in order. And then when you're done, you set the channel, but you also set this bit here. And that's like the end of sequence bit. Right? So it'll convert, and then as soon as it sees that one bit on it, it says, okay, I'm done.
And it does the converting like automatically set that or something?
Yeah. No. You when you're setting M control, when you're writing this, you're writing the channel into the first bunch of them.
Yeah.
But the last one of your sequence, you write the channel, but you also OR in this bit.
Okay.
And then you set it to convert in sequence mode. Yeah. And it'll automatically go convert, but it'll automatically stop when it sees that bit.
Okay.
So it'll do so you can do a whole bunch of conversions in one step.
Okay.
Right? So you do the start conversion and then you just wait for the fifth one or whatever to be done. And the first 4 will automatically be done. Like by the time you see the fifth one's done, then you can read all 5 of them.
Yeah. So I'm getting the feeling with the ADC, it really matters kind of like the order that you put in these controls then, right? Like in your code sequencing?
Well, to a degree. I mean,
like that one would have to be last compared to some of the other ones, right?
Yeah, in order. So you're going.
Yeah.
Yeah, because like we got the control 0 stuff, right? Here we'll go back to the code again. And I'm sure if I was a pro at this, there's like a way to bookmark it or something. But you see how we're setting M control 0? Well, you can put up to M control 31 there, right?
Yeah.
And so you can set the first one to be sample chan, and then the next one to be some other chan, and the next one to be some other chan, the next one to be some other chan, or end of sequence. And then it would automatically do those 4. And then here, instead of watching for the 0th bit, you'd watch for the 5th bit.
Yeah. So, okay.
You'd know when the last one got converted. And then here, instead of just reading something out of mem0, you could read something out of mem0, mem1, mem2, mem3, mem4. Boom, all at once, because they're all done.
Okay.
But in order to enable that, you got to put the conversion mode to be sequence instead of single.
Yeah. Okay.
And that's like, pretty well it.
Okay.